Before beginning this project, there are a few preferences that I've changed in this file. In firing up Houdini, this is the first time this copy of Houdini has been run, so all of the system defaults, Houdini defaults, are in effect, and there's a few of those that I like to change. They can be changed at any time to set your personal working preference or project requirements, but if you want to follow along and have everything look and act exactly the same as it does in the video, I suggest that perhaps you change these as well. So I'm going to go to the Edit Preferences menu, and the first item in the list is General User Interface. And there's really nothing that I want to do there or need to do there, so I'm going to choose the menu drop down at the top, and I'm going to choose 3D viewports. Now the first thing I'm going to do is change the tumbling method. By default it's the 80s style tumbling. I tend to like classic Houdini tumbling. You can test these out and decide which one that you like. The other thing that I don't care for is I don't care for the default homing being set to oblique. I change this to Z-axis homing, so when we home the viewport window you're going to be looking at a bird's eye view down the Z-axis. So I change those two. The only other one that I'm going to change here is Objects and Geometry. And by default, the default geometry display is set to Show Current Operator. I like to use Show Display Operator. So I'm going to choose Show Display Operator, and then I'm going to accept this menu, and those defaults are now in effect. Now the other thing that I like to do is I find that by default, until we put some lighting in the scene, and there is no lighting in the scene at this point, so we're using the default lighting setup, I find the specular highlight a little bit distracting and a little bit harsh. So you can change that in either one of two ways. You can click in the viewport window and press the D key to display the display option menu, or you can choose this icon down here with the eye on it, and the same display parameters will open up there as well. Go into the Effects folder tab, and I turn off the specular option. And then I'm going to say save this as default. I have to verify that yes, I do want to do that, and close the menu, and we're pretty much ready to go. Now the other thing that I don't particularly usually want is I usually don't want the construction grid shown in the viewport window. Most people are accustomed to that, but I generally turn that off, and particularly for this exercise I like to have it off because it can get a little bit distracting to have it displayed. Now many of you will know that if you use the H key to home, then the homing is still set to oblique even though we set the preferences to home down the Z-axis. So what you'll have to do is up here where the icon indicates that we're looking at the perspective 1 viewport window, if you left click on there and choose home, then you'll want to choose Z-axis here as well. And you can see that the viewport window is now snapped to homing down the Z-axis. Now those won't stay in effect though, because this is actually a desktop preference. So what you need to do now is you need to go up to the Windows menu at the top here and choose Desktop. And this is the build desktop that we're working on. It's already selected, but I do want to select the option that says Save Current Desktop. And again, I have to verify that I do want to do that. And now the oblique homing will be in effect each time you fire up Houdini. Now there's one more thing that I want to do in this file. As you work through this project, you're going to want to be able to look at the display parameters from time to time. And by default, there's not a pane tab at the top for that. You'll see that there's a pane tab for Scene View, Channel Editor, Render View, and Composite View. But I like to have the Details view at all times so that I can look at details anytime I want and not have to do much moseying around to find it. So I'm going to left click on the plus symbol at the top here and say that I want a new pane tab. So that's opened up a new pane tab, and Houdini by default set it to be Scene View. So now I'm going to click directly on that tab with the right mouse button, and I'm going to choose Details View. And now I have Details View panel as well. So I'm going to go back to the Scene View. Actually, with the Details View here as well, I want that to be in effect at all times, so I'm going to go to Windows Desktop, and I'm going to say Save Current Desktop. Once again, switch back to the scene view, and now all preferences are in effect. So now if I were to tumble the viewport window, and of course hit the H key to home, I home down the Z-axis the way I want. I've turned off the specular highlights so they're not quite so harsh until I get some lighting in there, and we're ready to go. So that's it, and we'll now start the project. Now to begin this project, we're going to need a curve that actually represents the crack that we want to create. And I've already created that for you and put it in the Geo folder in the project files. That's really the only file that I've supplied that you're going to need. But we need to call that in to be the profile, if you wish, of the crack that we're going to create. Now, over here in the DAG node layout window, you'll notice that it says object. We want to be at the object level. Now I notice sometimes that this is set to be composite or something, so just check that for a minute to make sure that you're at the object level. Click in the DAG node layout window, press the tab key, and we just want a geometry container. So that just lays down an empty geometry container, and I'm just going to rename this to be surface crack. And I'll double click to jump inside, and inside you'll see the file SOP. Now by default the file SOP is looking for a geometry file called defaultgeo.bgeo, which of course we don't want. So if you click on the little file folder icon and navigate to the project directory, we're looking for crack BGO. Accept it, and there it is. We have the profile for the crack. Click in the viewport window and H to home, and there's the profile for the crack. Now some of you may or may not know that you can middle click on any one of these SOP operators at any given time and get quite a bit of information about the geometry that's being passed through this SOP. This is particularly important because this is one of your best troubleshooting techniques. If something's not going wrong, or if something is going wrong, or if you're not sure of exactly how the geometry is being processed or what's happened, you can always check this and get a lot of useful information. So at this point, it's sort of important to note that we have 126 points on this piece of geometry, and we also have 126 vertices. Therefore, we know that there are no shared points on this geometry at all. We also have 11 primitives, 11 polygons. And if you're new to Houdini, that's an interesting concept as well, because every piece of geometry in Houdini is considered a primitive. So keep in mind that even if you had a cube, you might think that's one primitive. But for Houdini, it's actually 6 primitives, 4 sides, a top, and a bottom. So we know we have 126 points, 126 vertices, so there are no shared points, and we know we have 11 primitives, or 11 polygons. Now in Houdini, they're all numbered as well, and numbering always starts at 0. So we actually have primitives 0 through 10, inclusive, for a grand total of 11 pieces of geometry. Now the other thing that's worth noting here as well is that there's only one point attribute associated with this file as well. So you'll see it says one point attribute P4, and the P just simply stands for position, and we'll get into that a little bit later on. So remember, at any given time you can middle click and get all of this information on the file. The idea here is that we want to take this crack, think of it as a Christmas tree, where when you're getting ready to discard the Christmas tree, or sometimes even when you buy it, what they've done with the tree is they've pulled a bag up over the tree, down at the trunk, and pulled it up towards the top of the tree, so that all the branches are effectively moved towards the trunk to make it easy for you to transport. And what we want to do here is we actually want to map a color to all of these curves actually. So the color itself will actually start off at black at the bottom of the curve, and as it travels up to the top of the curve it'll turn red. And The percentage of red, or the amount of red that we've got here, will be used to vary the width of the crack. You'll see as we get going. So in order to do that, the first thing we want to do is we want to straighten this curve up so it runs directly up the y-axis, and we want to bring all of these branches and we want to pull them all towards the center y-axis. The problem right now, though, is that because these are all unique primitives, unique polygons, that when we try to do that, we're going to destroy the intersection point here, where the branches, if you will, are attached to the main spine of the curve. And we don't want that to happen. You want it to act as if these were actually branches on a tree, and they were growing off of this main trunk so that they can't move. Now the easiest way to do that, or well, the best way to do that, is to fuse the points together where these branches connect to the stem. So if I were to turn on the points for a moment, this little point display icon here, you'll see that there is actually a point. So if you were drawing this curve yourself, you would want to make sure you did the same thing. There's actually a point on the main spine itself, and the point for the branch, and when it was built, was actually snapped to that point on the main spine curve. So there's actually two coincident points here, one on the main spine and one on the branch itself. And that is responsible for the 126 points. So what we're going to do here is right-click on the output connector of the file SOP, and then I'm going to choose, actually a much easier way of doing that is to just do Tab and F, and that will allow me to get a fuse SOP, lay down the fuse SOP, wire those two together, display the fuse SOP, turn on the fuse SOP display flag, and by default we're in the consolidate folder. The distance is set to 0.001, which is going to work quite well. So there's really nothing that you need to change here. But if you middle click on this fuse SOP, you'll notice now that we have 116 points, but we still have 126 vertices. So we now do have some shared points because the points and vertice values are different. There are 116 points, but there are 126 vertices. So what's actually happened here is that Houdini has actually fused the point on the stem, or the main spine, with the point on the branches. So these points here are actually fused together. And the nice thing about that is that now when we squash everything up the y-axis, then none of these branches will move away from their connection point on the main spine, and that's exactly what you want. Now, the reason why the point count has dropped from 126 to 116 is that the option here for remove degenerate points is toggled on. Distance is set to 0.001, and that works well here because those points were so close together when the curve was built that it's easily consolidated those points together. So to create the tapering effect, we want to map a color to the main spine in each of the branches. The main spine will start off with a full component of red, fade off to black at the top, as I mentioned. And each branch then, it has to start with the exact same color value as that position on the main stem. The easiest way to do that is by using a strange little combination of the spring and lattice SOPs to get that to work. So we'll do that now, and we'll get it prepped for the color mapping. Okay, so to do that, I'm going to right-click on the output connector of the fuse SOP, and I know I want a spring SOP, so I'm just going to press S, and there's spring, and that'll automatically attach a spring SOP for me. It's already wired to the fuse SOP. I'll toggle its display flag on. And then this time, because you're not exactly sure how it's supposed to hook up, I'm going to lay down the lattice SOP as well, but I'm not going to hook it up right now. So I'm just going to click in the DAG node layout window to make sure nothing is active, press the Tab key, and L for lattice, and there it is, and drop an unconnected lattice SOP here as well. Now, for those of you who haven't dealt with Houdini a lot, you'll notice that most of the operators, or a lot of the operators, only have one input connector on them. In other cases, such as the lattice SOP, you'll see that there are 3 input connectors. Now, whenever you see multiple input connectors, the first input connector is pretty much always mandatory. The second and the third may or may not be optional. Often the first input's needed, quite often the second input is needed, and often the third input is optional depending on what it is that you're trying to do. So to find out what those are for, you can middle click on any one of those inputs. And if I middle click on the first input of the lattice SOP, you see it says geometry to deform. Second one is rest geometry, and third one is deform geometry. So we'll go back to the spring SOP for a moment, and I'm going to select it so that its perimeters are displayed. And the first thing I want to do here is delete the time increment channel. Now to do that, I want to right click directly on the name and simply say delete channels. Right? And when they're deleted, then the time increment value there will display as a value because the expression has been taken away. And I'm going to change that to 0.01. When you change a parameter in Houdini, notice that the parameter goes bold. And that's really nice because then whenever you're looking at an operator, you know exactly which one of the parameters you've changed and which one of the parameters are still at their default condition. Now I want to move into the forces folder. And external force is the one that we're after. And right now external force is set to 0, 0, 0. So effectively there is no force happening. This is where we can define the axes on which the force is going to be applied. So for the y-axis, I want to select that value and replace it with 1. So now the external force is going to be applied to the y-axis. I'm going to move into the nodes folder. Now in the nodes folder, the first thing we want to look at is the fixed point. And when the spring takes effect, and when we're moving all of these branches or squashing them up the y-axis, we want to make sure that it doesn't push the whole entire curve up the y-axis. So we want to anchor this very first point on the curve so that it won't be pushed up the y-axis. So I'm going to turn the point display off just for a minute to clear up the screen. And we can look at point numbers at any time whatsoever so that we can find out what number this point is so that we can specify the correct fixed point. So over here in the display icons, I want to toggle on point numbers. And now I can see that that actual very first point is 0. So for the fixed point, I'm going to set that to 0. So that point can no longer move. All right. Now the drag parameter, I'm just going to reduce the drag parameter. The default is 1. I'm going to reduce the drag parameter down to 0.5. And for this particular effect, for what we want to do, we want to change the spring behavior. By default, it's Hooke's law. We want to change that to be normalize displacement. And the only other option that I want to change is the spring constant. The default is 30. And I want to increase the spring constant to quite a high value. So I'm going to change this to 1000. Okay, so we have fixed points 0, drag 0.5, spring behavior, normalized displacement, and spring constant is set at 1000. Now normalized displacement is important as the displacement needs to be normalized to the original length of the spring. Alright, now we're ready to set up the lattice SOP. So if you click on the lattice SOP to display its parameters, want to move into the points folder, and there's an option for visualize specific point specific radii, which right now is grayed out. The reason why that's grayed out is that at this point Houdini doesn't have enough inputs for the lattice SOP to really realize what's going on. So if you check the first input again, that says the geometry to deform. So the geometry to deform is the geometry that's coming out of the fuse SOP. So I'm going to click on the output connector of the fuse SOP and connect it to the first input of the lattice SOP. The second input is the rest geometry. So in this case, the rest geometry is actually the geometry coming out of the fuse SOP as well. So I'm going to connect the fuse SOP to the rest geometry as well. then the third option is deformed geometry. And that's going to be the geometry that's deformed by the spring SOP. So I'm going to connect the spring SOP to the third input of the lattice SOP. And now when I do that, the visualize point-specific radii option is actually visible. So now I'm going to turn that on, so I'll be able to view the point radii and display the lattice SOP itself. So now you see a radii representation of the influence around each one of those points, and they're pretty huge at this point. We don't want that much influence, or the spring is just going to go absolutely crazy because they're overlapping so much and there's such a lot of conflicting radii influence there. So I'm going to use the slider on the radius perimeter and just back that off. And if you back it off to about somewhere around 1 point or 0.12, that'll work pretty well. And I don't need to see those point numbers anymore, so just to clean up the screen, I'll toggle them off as well. And we're pretty much ready to go with that one as well. Right. Now I'm going to go back to the viewport window, and I'm just going to home the viewport window. Use space H, and then you'll never have to worry about what mode you're in. It'll simply home up. And I'm going to start dragging the time slider across. And what you're seeing is you can see that the main spine itself and all of the branches are trying to find their way to the y-axis. And underneath that, you'll see a template of, if you will, of the original position of all of the curves. So if we get to frame 240, which is the length of the animation, you'll see that they're still not lined up. And you'll also notice that if you back the time slider back, it won't play in reverse at this point. Right, so if we move that up, you can see the springs oscillating and doing their number. Okay, but at 240, we don't have what we actually want for the deformed geometry. We don't have everything tight up against the y-axis. So what we need is more time for that spring to be able to do its job. So I'm going to change the default length of the animation to actually to 1200 frames. So if you come down here, global animation options, and we select this guy, we can see that the end frame is currently 240. I'm going to change that to 1200 frames. And just do an enter. I can close that window. And we do not want to stretch the channels. So you're going to say no in this menu. So now we have to go back to frame 1 and start the procedure all over again. And if you pull the slider up here now, you'll see that we're getting a pretty nice fit along the y-axis. And it looks to me as if somewhere around 902 frames I'm pretty good, but there's no problem there. Let's take it to the 1200 frames, and we know that everything's lined up very nicely, very tight against the y-axis. Right? So the next thing that we want to do is we don't want this spring SOP to have any other effect anymore. So we just sort of want to be careful. We want to lock this so that if we make any changes to it, it's not going to screw anything up. So if you look at the SOPs, there's a yellow flag here, an orange flag, a pink flag, and a blue flag. And the blue flag you use quite often because you're toggling to the display of the SOP on. The orange flag is not used quite as often. And I'm going to toggle that orange flag on, and that essentially locks the SOP. So the SOP now is frozen, and it can no longer do what it's, well, it won't accept any other changes. It's locked to the current changes, just as a safeguard that we won't change it later on. Any parameter changes here that you make would not have any effect. But once the SOP is locked, you have to be careful that you don't unlock it again, because if you had changed these values and then unlocked the SOP, those values will take effect and things will be different. But Houdini would warn you if you were about to change a locked SOP anyway. Now, the next thing I want to do is I want to be able to isolate the main stem from the branches, if you will. And the reason for that is that we want to apply the color, or the ramp, which is going to go from red to black, up the length of the main stem. And then we're also going to have to map each one of those little branches with the appropriate color as well. And it's going to be much, much easier if we separate those into separate them out into two groups, if you will. So the easiest way to do that is to use the delete SOP. So going back to the lattice SOP, I'm going to right click on the output connector. I'm going to press D, and there I have delete. Lay down a delete SOP, toggle its display flag on, and by default the delete SOP is set to delete selected. And should probably have shown you this before, but the beauty of Houdini is you can move up and down this chain at any given time. So let's display the fuse SOP again. And just as you were able to display point numbers, you can also display primitive numbers, and that's this icon here. So if we display the primitive numbers, you'll see that the main stem itself is primitive number 0. And the branches themselves are primitive 1, primitive 2, primitive 3, primitive 4, and primitive 5, etc. You get the idea. So what we're going to do here is go back and display the delete SOP. I don't need these primitive numbers anymore, so I'll turn that display off as well. And for the group parameter, I'm going to put in 0. So what you'll see here now is you appear to have a break in the stem. Well, the reason for that is what you've actually done is you've now deleted group 0 or primitive 0. So we've deleted all the we've deleted the main stem, and now all we have are the branches that have all been squashed up to that y-axis. So in actuality, what we want here is we want to change the operation from delete selected to be delete non-selected. And if you use the trick to watch the get the information of the geometry being passed through the delete SOP by middle clicking, you'll see that we only have one primitive, one polygon with 49 points on it. So that we know now that we've only got the main stem, and that main stem has 49 points on it. So the other important thing here to note in this information is that we have 49 points on this main stem, if you want to think of it that way. So those point numbers go from 0 through 48, and you already know that point 0 was down here on the space of the stem, so point 48 is up here at the top of the stem. And I need to find the position. I need to know where that top point is, and that's why I had you set up the details tab at the top. So if you select details view, and in the column here on the left-hand side, you'll see all of the point numbers. I'm just going to use the elevator slider here to go down to point 48, and we'll see that at point 48, we've got a value here of, on the Y position, I'm just going to move these. There, it's a little easier to read. So you can see on the Y position, we've actually got a value of 12.585. So that's where point number 48 is sitting on the y-axis. Now your value might not be exactly 12.585, but it should be pretty close to that. You don't have to get it dead on. It's not that important, as you're going to use whatever your value is. But if it's not relatively close to that, then I would go back and redo this spring again. So what I'll do here is pause the video and then start another one, so that if you need to go back and redo this one, then you can just fix that up. So in the event that you wanted to go back or needed to go back and play with that spring SOP to get that value closer to mine on the y-axis, we'll continue on from here. So I don't need the details view anymore. I have this value. I know what it is. I'll just go back to scene view again. And before I continue, I actually only want this animation to be 120 frames in length. So we can now change the frame length, and because you froze or locked that spring SOP, nothing will change, because if you remember before, back at frame 240, everything wasn't lined up the y-axis. So we took it to 1200 frames so that the spring would have enough time to line everything up the y-axis, and then we froze that spring stop. So we can go back and shorten the animation now. So I'm going to go back to frame 1, or frame 0. Frame 1 actually, sorry. And choose the global animation parameters. And for the end, I'm going to set this to 120, so we now only have 120 frames of animation. I'm going to say apply, and we do not want to compress the channels. So again, I say no, don't compress the channels, and I can close the animation parameters, and now I only have 120 frames of animation, and nothing, of course, is happening here because the spring stop is frozen. All right, so if we look at the information coming out of the delete SOP by middle clicking again we have 49 points, 0 through 48. We have one primitive, one polygon, but the important thing here is to note that we only have one point attribute. Remember I mentioned that before, it was position, and that attribute showed up in the details view, and that's how we were able to easily find the position of point 48 on the curve. Well, what we want to do here now, just to make your life easier, and you don't really actually have to do this, because when you need the position of that point, you could key it in, but then you always have to remember what it was. So there's a much easier and much more convenient way of doing that in Houdini, and you can do this at any given time, and that's the ability to create your own custom attributes, where again, as there's only one attribute associated with this curve right now called the point attribute, you can make your own custom attributes in Houdini and then use those whenever you want. And they're done with the attribute create SOP. So I'm going to right click on the output connector of the delete SOP, press the A key, and I can find attribute create. There it is. And I'm going to toggle on the attribute create flag. Now if I middle click on here now, I have 2 point attributes, position and attribute. All right, and attribute really isn't set to anything useful right now, but we'll do that now. So in the attribute create parameters, the first thing I want to do is I want to give this attribute a name. And I'm going to call that last underscore point. All right, we hate to have to type too much, so let's do last underscore PT, just short for point. Now the other thing to note here is when you're naming an attribute, you should get into the habit of following the convention that Houdini uses by default, and that means that all attribute names are in lowercase. So notice I have lowercase LAST underscore PT. Spaces are not allowed. Punctuation, other special characters are not allowed. The underscore is great. That's the one you should probably be using. All right. And then if you scroll down here to value, you'll see that the value is set, or the size is set to 1, and we'll leave that at 1. What actually happens here is if I middle click on the attribute create SOP again, notice that it says attribute 1, and then it has in square bracket attribute, and then in square brackets it has 1. That means there's only one value associated with this attribute, and that's all we need. So in the value field here as well, or in the value field here, that number you found, 12.585, that's the number that we actually want here. So we could set that to 12.585, and that would be okay. If we now look, we now have an attribute called last point, and it has a size value of 1. There's only one value associated with it. But actually putting in 12.585 almost defeats the purpose here, because we want to set up an attribute where Houdini will always find that last point, and whatever the value, the position of that point is on Y, whatever that value is, Houdini will pick it up automatically. So if we make any changes, we don't have to come back in here and change this value again. So what we would actually like to put in here is a reference so that Houdini can do all this on its own, and we don't have to remember that value anymore. We don't have to key it in or anything else. And the expression that we want to use is the point expression. Now we actually want to create the expression that will calculate this value for us automatically. The first thing we'll do is we'll write an expression where Houdini will find the value for point 48, which was the last point on the curve, and then we'll modify that so that Houdini will actually find what the last point number is and then the value for that. So in actuality, this expression will take care of any scenario where the curve has any number of points on it at all. Now, I don't want you to get too hung up on terms of having to rename SOPs, because generally, for the most part, the SOP name, for example, lattice 1, delete 1, attribute create 1, are generally what you want, because there's a very quick visual reminder of exactly what that SOP is without you having to remember what the pictorial icons and that sort of thing are. But there are some strategic SOPs in a network that it will be much easier for you to write expressions if you actually change their names to something that's a little more descriptive. So I'm going to actually change the name of the delete 1 SOP to be main underscore spine. I still know it's a delete SOP because I'm accustomed to the icon on the SOP, and once you've used Houdini for a while, you'll become accustomed to what a lot of these are. So I know that this is the delete SOP, but it actually creates or leaves me with only the main spine, and that's just going to make things easier in a moment. So I'll go back to the parameters for the attribute create SOP, and as I mentioned before, the expression that we want to write is a point expression. So I select the value and start keying in the word point. And as soon as I do, Houdini realizes when I get the PO in there that we're probably going to use a point expression. So Houdini gives me a list of all the available point expressions. The one that I want and the one that's most commonly used is the one at the top of the list, point point open parentheses, closed parentheses. So I select that, and Houdini puts in the open parentheses for me. Now the first thing I have to do is tell Houdini where to find the SOP that I want to query to get the point number from. And I have to indicate to Houdini that this is a string. So I do that by putting in an open parentheses. I follow that with dot, dot, slash. And then Houdini will give me a list of all the SOP names in this current SOP network. So you can think of $, dot, dot, backslash is moving up a directory. And think of the attribute create as a directory. So you are inside the attribute create SOP. By putting in dot, dot, backslash, you now move up a directory where Houdini shows you a list of everything else that's outside of that attribute SOP. And there's main spine, exactly the one that we wanted, and then we have to close that with an open parentheses again. Now the next thing you need is a comma, which is a delimiter. And Houdini's giving us an idea here of what the syntax wants to be. And it wants the surface node, and that's what we've given it, main spine. Now it wants the float point number. It wants the number of the point that we're looking for. So we're going to put in point 48. That was the last point on the curve. I need another comma as a delimiter again. Sorry, another comma. I have to get my typing right here. And now it wants to know what we're looking for. And remember, we're looking for position. And again, that has to be quoted so that Houdini knows it's a string. So I'll put quote, uppercase P, closed quote. Now where did this P come from? If you remember a while back, and I'm going to look at the information coming out of the main spine because that's the SOP that we're actually querying. And if I middle click on there, point attribute, remember I said that P stood for position. So that's why I'm using the uppercase P in here. And then I need another comma for a delimiter, and I'm going to use the number 1 and close that with a quote again. And Then if I click on the value field, Houdini has returned the value of 12.585, exactly what I wanted or what I had before. And if I click on value again to show the expression, double click in the field, some people get confused or don't understand where the 1 came from. Well, when I'm writing an expression where I want Houdini to find the position of point 48, Houdini's expressions don't really understand x, y, z. It understands 0, 1, and 2, where 0, 1, and 2 equate to x, y, and z. So in this case, I'm looking at the y-axis. If this value were changed to a 0, Houdini would query the x-axis, and if this value was changed to a 2, then Houdini would query the z-axis. So the easiest way to read this expression is to read it backwards. And basically what it's saying is look on the y-axis and find me the position of point 48 in the SOP called main spine and return that value for me, which you saw was 12.585. I'm going to click on value again, double click on the expression. Now the only problem with this expression solved the problem of having to key in the value on the y-axis of 0.48, but at this point, if the curve had more points than the 49, 0 through 48, then we would have to come back and we would have to update this. We'd have to remember where this expression was. We would have to remember to update this to, whatever it was, 56 points, 59 points, 100 points, or whatever. So Houdini also has a lot of its own built-in variables that we can use to do that for us automatically. I'm going to select the 48 in here, and I'm going to use $, and then I'm going to use uppercase N and P, and Houdini then starts giving me a list of all the variables that it recognizes that start with NP, and the one I want is NPT, number points. And if I use NPT, now what gets a little bit confusing is that if you switch back to the click on the value name to switch back into the display mode where you would expect to see 12.585, you're actually seeing 0 here. So this one's a little bit more confusing because it doesn't visually return the exact number until Houdini actually cooks down through this network, but it'll all work out in a minute. So now, if we look at the information of the attribute createSOP, we have the position variable and we have the last point variable. And now we want to use that, as I mentioned earlier on, to ramp a color along this curve. And we want the curve to start at black at the bottom and go to red at the top, for example. So to do that, we map this value to the points on this curve. And that's done with the point SOP. So if you right-click on the output connector of the attribute createSOP, press P, and we'll get a point SOP here. Toggle the point SOP's display flag on. And at this point, there's no change. But one of the attributes of the point SOP is point color. And currently it's saying keep color. So I'm going to click on that and say add color. And the curve now goes white. The reason for that is that the color here is set to white. And it's being driven by 3 variables, $CR, $CG, and $CB. Color, red, green, and blue. I want to delete those variables and put in my own. So you right-click on the color label and say delete channels. And now you'll see why it's white, because the values are 1, 1, 1. I actually want to change these to be zeros. So I'm going to do 0, tab, 0, tab, 0. Click on the color label again, and now I have an actual white or black curve. The entire curve is black, which isn't what I wanted, because I need to use the variable that I created, or the attribute that I created, to actually map the correct color onto each one of those points. Now I'm only interested in the red, so I'm going to double click in the red field, And what I want to do is I want to take the current y position and divide that by the value of the last point. And so what you'll do here is $, capital T, capital Y. So that's the translation on y. And what the point SOP is doing is it's looking through every point on the curve and it's finding the value of the y position for each one of those points. And we're now going to divide that by $LAST underscore PT. And what we wind up with is a curve that starts at black at the bottom and ramps up to pure red at the top. Now, the thing that you'll want to note, and that's important to note about this expression, is that although the attribute that we created, the attribute name, we specified as last underscore PT, all in lowercase letters. When we want to use that as an actual variable, then we indicate to Houdini that we're using that variable by prefacing it with the $, which we did here, and then the attribute name itself is uppercase, not lowercase. So the name is identical to what you specified, only you're using it here in uppercase letters. And so now we do actually have a curve that goes from black through to red. Now, in this particular case, we're going to be using this color to actually vary the width of the crack. So what we actually want, if you think of it for a moment, black is 0 and red at the top is 1. So this is now ramping up from 0 to 1, and a width of 0 is going to be pointed, and of course a width of 1 is going to be considerably wider. So we want to flip this entire color around. So now we're simply going to edit this expression to be 1 minus the expression, and now we have a curve that starts with a value of 1 for red and ramps down to a value of 0 for red at the top, giving us a curve that is now red ramping down through to black. And if you remember your algebra, of course division is done before subtraction, so it actually calculates this part of the expression and then subtracts that from 1. Some people like to be a little more explicit, and again, if you remember back to your algebra days, they like to bracket this, and that's a nice visual indication to them that actually whatever is in brackets is going to be done first, regardless of the order in which the algebraic mathematics would actually happen. So now we have the expression and we can move on from there. So this is where the detail view or geometry spreadsheet becomes extremely useful. Because rather than go through a complex project and find out that perhaps your expression didn't do exactly what you thought you wanted it to do or thought that it should do, you can look and see what the results are in the details view. So I had you set up a pane for the details view, which you can now click on, and down the left-hand column we have the point numbers from 0 through 48. So if we look at point number 0, which if you remember would be the point at the what you might think of as the root of the trunk of the tree, that was point number 0. So if we look at position on y, that's 0, and last point is 12.585. So color red equates to 1. Now let's take a look at point 24. Point 24 is sitting at 6.5 on the y-axis. If we divide that by the 12.585, then we're getting a value of 0.4833, which is, you know, pretty much halfway to being full red. And then if you look down at point 48, there's 12.585. Remember that was the position on y of the last point. Divide that by 12.585 and then we're getting a color red value of 0. So the geometry spreadsheet can be a real problem solver. You can check in here and see whether values are being returned exactly the way you want them to be. And I just quickly put a little something in Notepad here as well to explain what the expression does. So for every point on the curve, take the y position in space and divide that value by 12.585, which is the value of the position of the last point on the curve. And you can see we have 0.0 divided by 12.585 is giving us 1 minus that is giving us 1. And here we are at 0.48 giving 0. So sometimes people like to do this sort of thing. Just jot down 2 or 3 points, the beginning, halfway, and the end, that sort of thing, to see whether the values are being returned the way you thought they would be. Or just simply look at the geometry spreadsheet and you'll find the same thing. And then you can just go back to the scene view here. So we've actually got what we wanted. Now you may find, and if we look at detail view again, we actually are returning values here. Color CD0 is red. Again, CD0, CD1, and CD2, remember that's color red, color green, color blue, as opposed to CDR, CDG, and CDB. Keep that in mind as well. So we are returning values of 1 at the beginning, or 0 at the beginning, no, sorry, of values of 1 at the beginning, and we're returning values of 0 at the end. If the math didn't work out to be exactly 1 and 0, that sort of thing, maybe you went into a little negative value or something because of the math, or maybe this didn't actually equate to 1, that sort of thing. You could also edit the expression if you needed to using the clamp function. And what we could do here would be edit this expression to say clamp, and then what you'll need here is an open parentheses, and then at the end of the expression we would need comma 0, comma 1, and then closed parentheses. So what this has actually done now is it's basically said perform a clamp, clamping a minimum value of 0 and a maximum value of 1 for whatever value is returned from here. So hope that's helped with the expression part of things, and now we'll move on and start looking at getting the color mapped properly to the branches as well. Now that you've successfully mapped the color along the main stem, you now have to map the color along the length of each of the branches as well. And the color that begins, or the beginning color for each one of the branches, must match exactly with the color at the connection point to the main stem. This is going to require another network chain that branches off of the current network chain coming from the lattice SOP. If you use the right mouse button when you click on the output connector of a SOP, you actually insert a SOP into the current network chain. By using the middle mouse button, you can actually branch append a new SOP, creating a new network chain. So if you middle click on the output of the lattice connector and D, find another delete SOP, and you'll notice now that you've actually branched off a new network chain. The group again is going to be 0, but this time the operation is going to be delete selected. And if you turn on the display flag for the delete SOP, you'll now see that you only have the branches left. Now the attribute create SOP was used to assign a value to the last point on the curve, creating a variable called last underscore $PT. That variable, however, is not available in this new network chain because it's actually created in another network chain, and it's created later on in the procedure. So what you need to do now is you need to transfer that attribute from this network chain, or the old network chain, into the new network chain. And that's easily done with the attribute transfer SOP. So again, right click on the output of the delete SOP. We're looking for attribute transfer this time. And if you toggle the attribute transfers display flag on, you'll notice that the SOP immediately errors. The red marks on the node are indicating that there's an error. And the problem here is that there are two inputs into the node. The first node is the geometry to transfer the attributes to, and the second node is the geometry to transfer the attributes from. And at this point, Houdini has no idea which SOP is to be used to transfer the attributes from. So we need to connect the original attribute create into the second input of the attribute transfer. And now this network chain also has that attribute available to it. So you can proceed along with appending another point SOP. And the expression here will be the same expression that you used before to apply the point color to the main stem. So I'll toggle the display flag on for the point SOP. I'll change keep color to be add color. I'll delete the channels, set all those channels to be 0. And then for the red channel, we'll put in the expression again, which again was 1 minus $ty, position on y, divided by $last underscore pt. And you can see that we have color transferred to the branches now as well. It's very difficult, however, to understand or to see whether or not the color is correct or not, because we're still viewing the geometry in its deformed state, and we need to be able to see the geometry back in its original rest state. But before doing that, we need to merge these two SOP networks together for a final display. So I'm going to click so nothing is active, and use the tab key again, M to find a merge SOP again, and I'll feed both of these network chains into the merge SOP, toggle the display SOP on, and just so that things are easy to find later on, I'm going to rename this SOP to be merge underscore deformed. Now, if you check the information coming out of the point 2 SOP, that's responsible for isolating only the branches, you'll notice in this case that we have 77 points, 10 primitives, 77 vertices, and 10 polygons. So in other words, we have 10 branches. Those primitives will be 0 through 9, with a total of 77 points and vertices, so we know there are no shared points. Now this network chain, actually two network chains that merge together, they really serve no additional purpose in the procedure at all. They're simply there to deform the geometry and appropriately apply the point color, and now we'll actually go back and look at the geometry in its rest state and verify that the color is in fact correct. Now, if you're working with two monitors, it's particularly nice because then you have the option of displaying the node tree and the perimeter windows on one monitor, while you have a full screen view of the actual scene on another monitor. But when you're only working on a single monitor, screen real estate sometimes becomes very important. So there's a great little icon here that will take any one of Houdini's windows and expand it to full view. So I'm going to click on this icon here to full screen for a moment, and then set up to show the geometry back in its original rest position. Now, the important thing in this particular procedure, and the reason why this file can typically fail, is that you have to be extremely careful where you hook up the new SOPs. And if you think about it for a moment, we've read in the file, and that original file had 126 points on it. After the fuse, we dropped it down to 116 points, and then we fed that to the deformation procedure. Now, when we look at the rest geometry again, we have to be very, very careful that the number of points in the rest geometry matches identically the number of points in the deform procedure, so that the color can be mapped correctly. So what we're going to do at this point is take the two delete SOPs. One of them is called main spine, the other one is called delete 1, which I'm actually going to now call branches, just to keep things easy to walk through later on. And the easiest way to select these is just to band select them, and you can do a Control-C to copy. And I'm going to click on the layout window so that nothing is active and do a Control-V to paste them. And I'm going to rename these main spine rest and branches rest. Now when the SOPs are copied and pasted, Houdini has actually connected them to the lattice SOP because that's where they are originally copied from, and that connection isn't what we want. We want to connect these to the fuse SOP. And again, remember, this is very important because we want to make sure that the rest position has the identical number of points in it as the deformed geometry. So if you just right-click on the fuse, output of the fuse SOP, reconnect that to the main spine rest, and do the same thing with the branches rest. Now we actually have the original rest geometry, and it's coming from the fuse SOP, so that we know that there's no problem with mismatched point numbers. Now we want to take these two networks and merge them together as well. So I'm just going to do Tab, grab Merge that I've already used, connect both of these into the merge SOP, toggle on its display flag, and now I'll shrink this window back down so that I actually can see the result in the scene view window as well. And I'll just home that. Now, just to help you understand what's going on as you continue here, I'm going to move back over to the deformation procedure again. Now, if you look at the attribute create and the information that's coming out of there, we have 2 point attributes. We have P for position, as I said before, and we have last underscore $PT, which is the variable that you created to find the last point number. If you look at the information coming out of the attribute transfer, we have the same variables coming out of this as well. But if you look at either one of the point SOPs, and I'll look at point 1 in this case, we see that we now have a new attribute called CD, and there's 3 attributes there. So that stands for color diffuse, and the 3 indicates that there are 3 values which happen to be red, green, and blue. And in point 2, we have exactly the same information, and that information flows down through the merge SOP that we called merge deformed. So we have point position, we have last point, and we have color diffuse coming out of here. So now we need to take that color diffuse, that's the color that's been mapped onto each one of the points, and we have to bring that over and map it onto the geometry in its rest position as well. Now, the expression that you're going to use here is a little different than the first expression that you used, and yet the syntax is actually the same. Now, some people have a little bit of a difficulty when they first start writing expressions in Houdini, so I just want to review those very quickly. Now, when we were working in the attribute create SOP, where you wanted to create a variable called last underscore PT, and you wanted to assign the value of the last point on the main branch to that variable, you used the point expression. Now remember, P was a built-in variable in Houdini that stands for position, so P is position. So we were working inside of the attribute create SOP, and we said ... which said move up 1 directory level. So in other words, we exited from the attribute create SOP, and then we searched for the SOP called main spine. So find me the SOP called main spine. When you find that SOP, look at point, because this is a point expression. Look for point 48 and return its position on the y-axis. and that returned us the positional value of point number 48. The problem, of course, there was that we would always have to remember to change this last point designation should we change the curve in any way, or if the number of points on that curve changed. So we just expanded that expression a little bit by substituting 48 with the variable, again, built-in Houdini variable, $NPT, where NPT is the number of the last point. So these expressions did exactly the same thing, only this expression was a little more functional than this expression because we don't have to worry about actually specifying the point number. Houdini can find that point number here itself. Now in this case, things are a little bit different because we're using a point SOP again, but we're using a variable called $PT. And $PT is the point number again, but what it'll do is it'll have Houdini look through every one of the point numbers. And CD is color diffuse, and in this case we're using 0 because remember, just as we used up here, 1 equates to Y, where 1, 2, 0, 1, 2 is XYZ, and down here 0, 1, 2 is red, green, blue. So in this case, if we're working inside of the merge SOP, which is actually the one that we called here, merge 1, if we're inside merge 1, we're telling Houdini again, exit from the merge SOP and find me the SOP called merge to form. When you get there, look at each one of the point numbers and find its color diffuse value for red. Now, this expression here is actually known as a relative expression. It's relative to where we currently are. So we just do .. and we move up a directory. And that'll work. You can use this expression. That's not a problem at all. This expression is known as an absolute reference. So what this one is doing is you see /obj. So we're telling Houdini to go back up to the main object level. And at the object level, find the object node called surface_crack, dive inside that and find the SOP called merge deformed, and then when you get there, of course, look at each one of the points, find its color diffuse value for red. So we can use either one of these expressions. This one's a little more typing, this one's a little bit easier, so this is the one that we'll use. Okay, so point SOP will be used to get that color information from the deformed network and bring it over here to the rest geometry. So I'm going to right click on the output connector of merge, get another point SOP, toggle the point SOP's display flag on, and then I'll let Houdini do the work for me as I build the expression. So we're going to again change keep color to be add color. Delete the current channels, set these channels to black, so 0, tab 0, tab 0, and then we'll start building an expression in the color red. And that's going to be point, open parentheses, .. whoops, I forgot the quotes, quote, .. and we want to look for the SOP called merge deformed, closed quote, comma, as mentioned before, $PT, and again Houdini helps us out, there's $PT, comma again, and quote, and we're looking for CD, color diffuse, closed quote, comma, and 0 for color red. And we can see that the color has been mapped onto the branches of the stem as well. And if you zoom in and have a look around, things are looking relatively good at this point. We seem to have the correct color for the connection of the stems. These guys are fading off very quickly to black. And these guys here don't seem to be fading off to black, so we need to look and find out what the problem is there. Okay, so we do have color transfer over to the branches, and it looks as if the value being picked up for the connection point on the branches is actually working out okay. The color at the connection point for the branches in the main stem appears to be correct, but the branches aren't fading off to black. They're not doing what we want. And the problem there is actually I built this in because sometimes it's better to have to troubleshoot than just follow along and everything works out. So if we think about this for a minute, if I display the main spine rest and turn on point numbers, these points start at 0 and travel all the way to 48. Now if I look at the branches, however, in the branches rest, I have point numbers here that are going from 0 to 9, and then the point numbers here are going from 10 to 17. Here, for example, they're going from 61 to 65. So the thing to understand about points, and when you're using the point expression in a situation such as this, is that point numbers do not regenerate themselves. So every time you've got a separate primitive, and here we've got 10 primitives, 0 through 9, each primitive does not start at 0. So that's problem number one. And the second problem is that the point expression is looking for the last point on the curve, and it's actually looking at the main branch, and it's looking for the positional value of 0.48. Well, in this case, that causes a huge problem because 0.48 happens to be on this branch over here. So the actual expression that we created here is not going to work well at all, and we're going to have to find something different. And the answer is to actually map color to the vertices instead of the points. And the reason for that is that vertices do regenerate. So in terms of vertices, the vertices for every primitive always start at 0. So we'll look at that and fix up that expression now. Okay, so I'm going to display the points up again and turn the display of point numbers off again. We don't need those. And just to review the problem for a moment, you may want to review this document, understanding the problem. The main spine is a single primitive with point numbers beginning at 0 and increasing in order to 48. So the calculation and interpolation between the colors was really easy. If you think back to the expression for a moment, we took the y position and for each one of the points and divided that by the position of the last point. And then, of course, to flip the colors around, we did 1 minus that result. So you can see that for point 0, we returned a value of 1, and for point 48, we returned a value of 0. So basically, it was easy to create a linear ramp from 1 through 0 along the length of the spine. In the case of the branches, however, there are 10 separate primitives, and each of these primitives vary in length. So you're faced with two problems. First, the last point position for each branch varies from branch to branch. So the value passed by the $ last underscore PT variable will not work for each individual branch. In fact, it won't work for any of them. None of the branches have 49 points. Secondly, point numbers, as I mentioned, do not recycle. So each branch does not start at 0. Each branch starts with the next consecutive point number from the previous primitive. Again, if you considered the left bottommost branch, the point numbers on that branch are actually 10 through 17, not 0 through 9 as you might have expected. So the expression you used for the spine calculation does not take these two variables into account. So the vertex op comes to the rescue. The thing to remember is that vertices do reset and always start at 0 for each new primitive. So this takes care of the problem encountered with the point numbers not beginning at 0. And a slightly more complicated expression based on the vertex position rather than the point position will take care of the varying length of the branch. So that's what we'll look at now. So to show you a few more things and just make this a little bit easier, I'm going to expand the SOP window or the DAG node window to full screen view again. And the problem here is with this point SOP in the branches network chain. We can't use a point SOP here because the point SOP won't understand the vertex expression. It only understands point expressions. So we could delete this point SOP and replace it with a vertex SOP. That's not a problem at all. Or you can make your life even easier simply by right-clicking directly on the pictorial icon of the SOP itself, and we can replace this SOP with a different SOP. You can use whichever technique you want. But if I right-click, there's an option that says change type. So I'll select change type, and from the pull down menu here I'll change this type to be a vertex SOP. And when doing that, you have the option of keeping the parameters, keeping the name, or keeping the network contents. In this case, I really don't need or want any of them. I don't want to keep the parameters, so I'm going to toggle that one off and say accept. And that simply changes this to a vertex SOP without you having to delete the current point SOP and then put the vertex SOP back in. Now, I'll expand or reduce this back to regular view again. And in the color expression, I'm now going to replace this with that expression that we looked at. Now just be very careful how you type this in. The parentheses are going to be very, very important. So we want open parentheses 1 minus $ VTX, and again Houdini helps us along. And then I want to divide that by $ N, and again Houdini tries to help us along. There's $NVTX minus 1. I need another parentheses there, and I need another parentheses here, and then I'm going to multiply this by open parentheses 1 minus $TY divided by $, and again Houdini helps us out, last point, closed parentheses, enter, and Houdini's given us an error. If I middle click on the node, I have a bracing error, and that's very typical. Bracing errors typically indicate that you have forgotten an open or closed parentheses. So I need to check this again. So I have open parentheses 1 minus $VX divided by, and there's where I'm missing the parentheses. So I need this one, close that down, and we'll see where that takes us. Now this still won't be correct because in the rest portion of the SOP network, Houdini's actually doing a point color transfer, and it's not doing this vertex color transfer. So the vertex expression was important here to sort out the problems that we had with the differing point numbers and that sort of thing. Now the next step here is to take these vertex colors and put them on to the actual point. So you're going to right click on the output of the vertex SOP, drop in a point SOP, and here again I'm going to say add color. I'm going to delete the channels. I'm going to set these channels to 0, 0, 0. And for the color red, I'm going to use $CR. And now if you look back at the rest geometry, we've got exactly what we need. If you look at this, we now have a good color match where the branches connect to the main stem, and you can see that each one of these branches are fading off to black, and that's exactly what we're going to want. At this point things look good and you're pretty much on track to continue with the tutorial. If you're having trouble at all, if the colors don't match up properly or if things don't look quite right, then the first thing I'd do is go back and very carefully check your expressions. That's about the only way or the only area that you're really going to get into trouble here. If your expressions are correct, then you should have the same display as I have here that you see in the video tutorial. Now, this next step is totally optional. You do not have to do it, but it does improve the look of the file. In looking at the curve right now, although it is a polygon curve, I do find that it looks to be a little bit too smooth, perhaps a little bit too NURB-like for crack geometry. So I'm going to use a random expression to just put some randomness through the points to make this look a little bit more blocky, if you will, as a crack might appear. So this could be done in the same point SOP that you already have, but sometimes I like to use additional point SOPs or additional SOPs just to isolate particular effects that have been applied to the file. So to continue on, I'm just going to right click on the output of the 0.3 SOP here, the last point SOP in the chain, and insert another point SOP, and maybe we'll just rename this to say randomize points, perhaps, just so that you know what that point SOP is doing. And a toggle its display flag on, and I'm going to add some randomness to the X and Y positions of the points to make this look a little bit more polygonal, a little bit more like a crack might look. Something that I haven't shown you before that you might find useful is just click inside the positional TX field and use Alt-E. That'll bring up an expression editor that you might find a little easier to enter in some of the expressions. And this expression is going to be $TX. That's the variable that's already there for you, indicating the translation on X for each one of the points. And I'm just going to say plus rand, R-A-N-D, open parentheses, variable $PT, plus 40, closed parentheses, times 0.1 minus 0.5. The nice thing about the expression editor is that you can actually tell Houdini to apply the expression. And there's a message center for errors down in the bottom of the window here. And if it reports nothing, then there's no problem with your expression. It's valid and things are ready to go. But if you had left out an open or a closing parentheses or had some other kind of mismatch or variable that wasn't understood, then the errors would be reported down here. So you could quickly go back up and correct those, apply it again, and then when you're happy and everything seems to be working just fine, you can hit accept and the expression is entered into the field for you. Other thing that you can do is I can take the expression that's already there and I'm just going to copy the plus rand, etc., do Control-C to copy that, click on position again, double click in the Y field this time, and just to save some time I'll paste it in there. So the expression is the same, but this time instead of doing plus 40, I'm just going to do plus 3, enter to accept that, and you can see that it's now looking a little bit more polygonal, a little bit more like a crack would. And if you check 0.3 and 0.4, you'll see the change. Now this has created a bit of a problem here because if you notice, now the branches aren't connected onto the to the main stem. Okay, because we have done some random movements on the x-axis, it's actually shifted those on the x-axis so they don't line up exactly properly anymore. So you want to watch out for stuff like that when you're moving points around. But a really easy fix for this is to fuse the points together before we do the randomization. So I'm going to go to back up to point 3, and that was the point SOP where we applied the color. I'm going to right click on the output connector and choose a fuse SOP again. Put in the fuse SOP, and by default, as you know, it already does a consolidate points, any points that are within 0.001 of each other. So I really don't need to change anything there at all. If you display the randomized points again, you have the effect, and now because of the fuse, those points that were moved off and the branches weren't connecting with the stem any longer, with the main stem, that's now been fixed. Now this has also caused a positional shift in the entire curve itself. It really doesn't matter in this file whatsoever, but if you wanted this crack to be at a specific location on a wall, for example, it was initially lined up at 0, 0, 0 in world space, and perhaps you want to keep it that way. So a very easy way of shifting that around and getting things back to where they were again is just to append a transform SOP here. So I'll right click on the output of the last SOP, T for there's transform, lay down the transform SOP, and you'll notice when you lay it down the SOP becomes active. I'm going to turn the display flag on, move the cursor over into the viewport window, and then press the enter key. And what that's going to do is display the transform handles for you. So it's a really nice, easy, interactive way of just readjusting the geometry in the viewport window. So I'm going to grab the X translation and just drag that back over to X. Click on Y, move that up. And at this point you're actually no longer in view mode, you're in transform mode. Most of you will know that the cursor is changed to a selection handle instead of a view manipulation handle. So I'm going to hold down the space bar while I just tumble the viewport a bit, and then I can just do some final adjustments here, tumble around and check the x-axis. And things look pretty good. Everything's lined up again. Now, once again, at this point, you're now you're inside the transform SOP, and you're actually manipulating the geometry. You're no longer manipulating the view. That's why I had you hold down the space bar, because you'll notice when you hold down the space bar, you temporarily go back into view mode so that you can manipulate the viewport window. And at any given time, to exit the selection mode, then just press the escape key. The transform handle is gone and you're back into regular view mode where your cursor is now manipulating the view again. And then I can just do H to home the viewport window, or if it was manipulated again, there's no harm in doing space H either. It's the same thing. So all is good at this point, but at this point, you still have nothing more than a curve. So the next step is to convert this curve to surface geometry. Particularly easy way of doing that is to use the polywire SOP. So click on the output of the final transform SOP. And typically what I've been doing is having you use a key to look for a particular SOP. But you'll also notice they're broken into groupings here as well. So I could go to poly, and this gives me just a listing of all the poly tools, and I could select polywire here and lay it down in the node window, toggle its display flag on, and immediately the curve has actually been converted to a polygonal surface. So working with the polywire parameters, the only thing that I'm really going to change here right now is just the segments, and I'm going to increase the segments to 2 just to give a bit more resolution to the surface. Now the whole idea behind this, building this and doing all this color mapping, was that we want this actual crack to be able to creep across the surface over time. And as it creeps across the surface over time, it's going to continually widen. So as time goes by, where the crack initially started, it's going to be quite wide. And the crack at the ends of each branch, for example, they're going to come to a rather sharp point. And that's why you did all this color mapping, so that you could affect the width of the crack over time. So to start off, First thing you're going to do is go up to the wire radius parameter. And the wire radius parameter, as its name implies, is really just the radius of the wire surface that we're converting this curve into. And I'm actually going to double click in that field and just use the variable $CR, color red in there. And immediately you can see that something has happened. There's obviously a problem here. It's worse for sure, but you can see that the taper effect is working. The problem, of course, is that $CR is returning values from 1 down to 0. So here we have 1 unit, and at the end of the branches we have 0. So they come to a nice point, but the crack is far too, the radius of the crack is far too large. So it's crossing over itself. And so we'll just modify this expression a little bit. So we're going to edit the expression to be $CR multiplied by 0.065. That's a fairly good value to use, and the crack actually looks quite good. Much better in terms of size. However, if you think a crack like this might take shape over time, the crack is likely to begin as a very fine fissure. As the length of the fissure grows and progresses along the surface, the beginning of the fissure would widen up, and it would also widen up over its length over time. So, easy way of doing that is to use another built-in Houdini variable called $F. And $F, for those of you who don't know, equates to current frame number. So I'm just going to make some edits to this expression again. So it's now going to become open parentheses $CR plus $F. And I need a closed parentheses there to make things happy, and then multiply that overall effect again by 0.065. So at frame 1, and if you then pull the slider across, you'll see that $F is doing its job. Of course, it's creating a far too great a radius far too fast. So by the time we even get to frame 1, things are getting out of control. And the second thing, of course, is it's not tapering off over time, but we'll deal with that one in a minute as well. So we want to make one more edit to this expression. And what that's going to do is going to take $F, and I'm going to divide that to slow it down. So I'm just going to divide by 120. So now I have open parentheses $CR plus $F divided by 120 times 0.065. So now at frame 1, things look pretty good. And as you advance through the frames, you can see that things do widen. The radius does get larger, and it's happening at a relatively decent rate. But of course, we still don't have the taper effect that you really want, so that'll be the next thing to control. So as you work through the edits to the expression here to create the tapering effect the way we actually want it in this example, I want you to understand what's happening in terms of the mathematics behind the expression as well, and it'll make it easier. The expression really is not that difficult. So at this point, make sure you're viewing 120, and the effect looks okay. Although we don't have the tapering effect that we actually want at this point. So let's just take a look at the math behind that for a minute. Now consider what's happening at frame 120 at the beginning and at the end of the main spine, just as an example. So we can think of just having the main spine there, and at frame 20, the 0.0 is at the start of the spine, and we know there's a color red value there of 1. So if we look at the expression at this point, we've got 1 plus 1 times 0.065. So we've got 2 times 0.065, giving us a starting radius of 0.13. Now if we look at frame 120 and consider the 48th point, or the end of the spine, color red there is 0. So now we've got 0 plus 120 divided by 120, or in other words, 0 plus 1 multiplied by 0.065, giving us a radius at the end of the spine of 0.065. So we wind up with a radius at the start of 0.13 and a radius at the end of 0.065. So there is some tapering happening, but at frame 20 we want a radius at the end of the spine to be 0. So we're just going to make some minor edits to this. So if we edit the expression to be $CR plus $F divided by 120 minus 1, we're going to get pretty close to what we want. Because if you consider at frame 120 then, where color red is 1, we've now got 1 plus 120 divided by 120 is 1, and we subtract 1 from that. So basically we've got 1 plus 0 times 0.065, giving us 0.065. Now at the other end, where color red is 0, if you look at the math behind this now, we've got 0 plus 1 minus 1. So we wind up with 0 plus 0 multiplied by 0.065, giving us the 0. So now at frame 120, all is good. But we're going to have a problem when we go back to frame 1. So at this point, let's go back to frame 1 and just pull the slider through. Sorry, I haven't made that edit yet. Minus 1. And now the problem is at the beginning of the animation, we've actually got the reverse of what we want. And over time, the effect actually reverses. It almost appears to flip halfway through, and then we get what we want. Well, the problem here, of course, is that halfway through the animation, we're getting negative values. So there's one quick edit left to do, and that's to clamp this so that the values can't go into a negative value. So I'm just going to put clamp, and we're going to leave the $CR plus $F divided by 20 minus 1. But then I need to insert comma, specify the minimum clamp to be 0, comma, and the maximum clamp to be 1. So the expression now reads, if we just look at the math here for a moment, I've now got clamp, open parentheses, $CR plus $F divided by 120 minus 1, comma 0, comma 1. But 1 will work, but we really would like to drive that by the color red, whatever the actual maximum value of color red is. Maybe it wouldn't actually go to 1, maybe for some reason you don't want it to actually be 1. So we can just substitute that for $CR as well, but either way that will work. So let's just take the 1 and substitute that for $CR. And now basically you've got what you want, because when you think of it at frame 1, you don't want to have anything happening at all. You don't want any radius on the crack at all. And then as time goes by, the crack actually starts to creep through the surface, and it tapers off to 0 radius, which is what we want at the end. So we're almost there with that, with just a few more edits. So at this point, the effect is actually working. But we have something now that resembles something much more like a twig if I just look at this in shaded mode. And what we're really after is something that represents a crack. Although this could be interesting as well to grow a twig or a vine over time, that sort of thing. But for this exercise, we want a crack. I'm going to go back to frame 1 for a moment. Or actually, let's stay at frame 20 because it's going to be easier to visualize what's happening. And I want to work at this in wireframe mode. And I'm just going to zoom in a little bit. Now, as a result of the polywire conversion, or taking this curve and changing it into a polygonal surface, I probably do wind up with a few degenerate polygons and that sort of thing. So it's a really good idea to clean this up after the construction. And that's pretty easy to do as well with the cleaning tool. So if I right click on the output of the polywire, and I'm going to go into polygon folder again just to give you a chance to get accustomed to that. And I'm actually looking for the poly tool called clean. And I'll drop in clean, toggle the display flag on, And the defaults are going to be fine at this point, where we remove degenerate polygons, remove unused points. So if we look at the information passing through the polywire, we can see we have 1112 polygons, and after the clean we're down to 1053 polygons. So the clean has helped to get rid of some degenerate polygons that could give us some rendering difficulties and that sort of thing. Now the key here to changing this into something that looks more like a crack, and one of the reasons why I wanted this to actually be lying on 0 along the z-axis, is that it makes the clip really easy to use with most of the defaults in place without having to do too many changes to the clip parameters. And it'll work like this. Right click on the output connector of the clean, and I don't quite remember which section clip is in, so I'm just going to use C and get a clip. Toggle the display flag on. Now what the clip SOP does is it's really just a clipping plane that can be positioned anywhere in 3D space to clip the geometry. And the origin of it is right now is at 0, 0, 0, and that's what we want. So you can think of a clipping plane sitting at 0, 0, 0 in the world. And in the direction, it's going up the y-axis right now, which is not what I want. So I want to make sure that I set the direction on y to be 0 and the direction on z to be 1. And it actually has now clipped the bottom off. So we almost have an inverted crack at this point. So I want to change the keep option. The keep option is primitives above the plane. I want to change that to be primitives below the plane. And now I have something that looks much more like a crack. And if you look at it in shaded mode, it's beginning to look much more like a crack. Now there isn't much depth here to the crack either, so I think one more edit that I'll do while I'm here, I'm going to right click on the output connector here, T for transform, get a transform SOP, toggle its display flag on, and I'm just going to scale this 3 units on the z-axis as well. So that'll give some depth to the crack. So we're pretty close to being there. The next step is actually going to be to build the surface around so that it actually looks like a slab of concrete perhaps, or a slab of plaster or whatever that the crack is going to creep through. And if you just play through now, we have something that's starting to look pretty good.